Hello, everyone. Let's begin this lecture. And in today's lecture, I will be talking about counting and probability. I've already done two lectures on counting before, and here I want to link it to probability. And by that, I mean I want to tell you how counting is used in probability, how the concepts of counting is used to calculate probability. So, this is something I have told earlier as well. Counting techniques are very useful when the sample space is finite. It's not that it's useful, it is where it is actually used. Counting techniques are mostly used when the sample space is finite. And generally, if you have any random experiment, you have a sample space, right? And the sample space has a list of elements. If you talk about a finite sample space, a list of elements or a list of things which can happen if when that experiment is taking place. And if all of the outcomes of that, say I have the sample space S and it has I1, I2, these are the possible outcomes, all right? And if I say that each of them are equally likely, what does that mean? It means that suppose we have done some examples, right? Rolling a die. When you roll a die, the sample space is 1, 2, 3, 4, 5, 6. When you toss a coin, sample space is head, tail. Now, I can say that the outcomes of experiment are equally likely when any of these can happen. And it's not that any one particular outcome is more likely than other. Like when I roll a die, any of the six numbers can come. I can't say that 6 will come with there are more chances of 6 to come, or there are more chances of 1 to come, unless it's like the die has some issue. But if you have a fair die, if you have a fair coin, then there are equal chances of uh, any of the occurrences to happen at a given point. So, it's safe to take this assumption that the outcomes of an experiment are generally equally likely, unless it is explicitly mentioned in the question. And hence, in those cases, probability just reduces to counting. And if I want to find the probability, or by probability I mean chance, of a given event A to occur, A, and what is an event? An event, we have done this earlier, an event is just a subset of a sample space. It is basically something that we are interested in. For example, if I roll a die, yeah, I say what is the probability that I get an even number. So the even number is 2, 4, 6. This is an event that I'm interested in at that point of time. So for finding the probability of any event, it is just reduced to a counting problem. You find the number of elements in that event A and divide by the number of elements in S. So for any task, what are the total number of different things that can come? So while rolling a die and while tossing a coin, it is very easy to write the sample space down because it is 6 elements, 2 elements, right? If I'm talking about some, and we'll come to an example just after this that will make it clear. If you have a sample space which has like a lot of elements, it's not physically possible and honestly, it's very unnecessary to write down each possible outcome, right? So we just want to count what are the different outcomes that are possible, and on the top is what are the different number of outcomes which actually interest us, and you divide the two, and that gives us the probability of that event. And I've added a side note here that for large sample spaces, the counting techniques might be used to calculate both the numerator and the denominator of the expression. So if we have large sample spaces, as I said, not useful to write down everything and then count it. You just need the count, all right? And that's why we've done the counting techniques. That will really help us in finding probabilities. So, the probabilities of events can be simply calculated by counting the number of outcomes in the event. That is what we have to do. So we have all the prerequisites now. We know how the probability has to be defined. We know counting techniques. And we know the different nuances involved with counting techniques. So we just now have to, based on the question, understand what particular counting I have to do and find the probabilities. All right. And I would like to end by saying that there is one core intuition, which is think like this, and that will summarize whatever I've told you on the top. Is that out of all possible equally likely outcomes, how many outcomes are favorable? And by favorable, I mean based on the question you're asked and based on what you are interested in, that is an event. You have to find the number of outcomes that are favorable to that event and divide it by the total number of outcomes. That is the probability, right? Let's dive into an example. I have taken many sub parts to this so that we go from an easy level to a more difficult level, and you get to understand different counting strategies that we have to take while finding probability. So, yeah, one thing I want to say, whenever you talk about probabilities, whenever you have probability sums, you will have definitely come across a playing cards problem. There's always a deck of 52 cards and there's something going on there. So that's how I have also started. This is the first question I'm doing on probability with you, and I have started a deck problem just so that you get a feel of probability. So there is a standard deck of cards. For anyone who doesn't know, a deck of cards has 52 cards. There are 13 cards of each. There are 13 cards of one type. So there are 4 different types of cards, and there is a diamond, there is a club, I don't know there is a heart, and I think there's a spade. These are the 4 symbols, and for each of these symbols I have numbers from 2, 3 till 10. I have a jack, queen, king, and I have an ace. So 4 and 9, 13. All right. So I have 13 of diamond, 13 of this, 13 of this, 13 of this. So 52 cards in total. Okay. Now from those 52 cards, I have to choose 5 cards. They're saying that all hands are equally likely, which it usually is. If it is not explicitly mentioned, if you have 52 cards, then you're picking 5 from it. Any card can come. There is no such thing that one card has more chance of coming than the other card, right? But to be more precise here, I have mentioned that the hands are equally likely. And secondly, I'm choosing 5 cards. Order does not matter for me because it's like I'm playing a game, all right, and I'm giving 5 cards each to each person. And suppose there are 15 people, I'm giving 5 cards each. The person is just interested in what cards I have, all right. The person is not interested in what order I get the card. That is not relevant for the game also. So, and without replacement for sure. So I unordered, so this is an unordered without replacement problem. Okay, and we have done this. Generally for this we go to combinations more. We are interested in combinations, which is if I have n, so in my case I have n is equal to 52, which is my cards, and my r is equal to 5, which is the number of cards I am picking. Okay, and if I am just I have to choose 5 cards from the 52 cards, then what are the total number of different cards I can get, given that I don't care what is the order. I'm not replacing any card. I'm just taking 5 cards one by one. So in that case, this is the total number of outcomes, which is 52 factorial, and we've defined this. So NCR is n factorial, n minus r factorial by r factorial. So 52 factorial and 47 factorial by 5 factorial. Okay. So this actually solves our first problem. How many different 5-card poker hands are possible? So if I write the first part, it is 52C5. I don't need to solve this, but it is a big number. You can definitely imagine this, right? I don't have to write everything down. I know that this is the total number of outcomes that are there. So this will be my denominator in all the probabilities I'm calculating. Now, this is where we are calculating the probabilities. Let's see. What is the probability of all hearts? So I have defined, right, we have 13 of each, and the question is, what is the probability that all the 5 cards that you pick are hearts? So denominator is fixed, it is this. Now if I want to get all hearts, I know that my choice must be from those 13 hearts only. I should not choose from anything else. So 13C5. Any 5 choices from those 13 heart cards, if I get, that is my favorable event. So 13C5 will tell me how many different picks you can make of 5 cards each from my heart 13 cards. And this is what we want in the numerator, right? This is our favorable event subset. So the probability is number of elements in event A by number of elements in the whole sample space, and hence we have calculated our first probability. So congratulations on that. I hope you understood what we have done here, because this is going to get harder with each passing problem. So let me know in the comments if you have any questions, if there is any other problem you want me to solve. We can go through that. All right, next question. Exactly one is. So now the difference here again, the denominator is this. Now the difference from my first problem, from this to this, is that I am just saying that I want one ace, and the other 4 cards I don't care. It can be anything. Like here I told you that all the 5 I want a heart. I don't care what heart, but I want a heart, right? Now here I am saying is that I want one ace, and I know there are 4 aces. So as we mentioned here, we will have one of each. So we have total 4 aces, and I can take any of the 4 aces. So 4 say 1, and then whatever, so consider this as 2 tasks. Task 1 is choosing an ace, task 2 is choosing the other 4 cards. Now since I have been told in the question that my 1 has to be an ace, so I have to be sure that 1 is from those 4 ace cards. All right, so this is my task 1, this is done. And now I'm talking about the second task. What about the other 4 cards? And the other 4 cards, since I've told that it has to be exactly one ace, the other 4 cards can't be an ace and can be anything else from the 52 minus 48, which is the 52 minus 4, which is 48 cards. So next problem has these many, can be done in these many ways. All right. So by this is actually the fundamental theorem of counting going on. This was my whole task, and I divided it into 2 subtasks, of which I know like how many ways they can happen, and so I just multiplied it, and this is our probability. All right, let's go to question 3 now. Question 3 is, now I'm saying I need exactly 2 aces. So I'm not explaining, this is very similar to the B problem. So I'm just writing down the answer and You can pause the video and try to do this yourself before looking at the answer. And again, let me know if this is not clear. Okay, let's go to the next problem. Now I'm saying I get exactly one pair of one kind. So what I mean is that I mean to say that, so I have these, right? So I'm saying that I get one pair of either diamond or this or this or this. So I should get two of these, or I should get two of these, or I should get two of these, or I should get two of these. All right. No, sorry. I think I said this wrong. Let me just rephrase. This is not what they're asking. What they're asking is that I either get two aces, two twos, two threes. Like this can be any. It can be any of the four these card types, but it can't be. But it has to be the same number. All right. So what is the probability that I get exactly one, just one of these? All right. So now I have 13 options, right? There are 13 different types of numbers that are there. So out of those 13, I choose one, okay? And whatever one I have chosen, say I get an ace. Now I have four aces, all right? And I have to choose four of the two from those four aces. All right. So now I have my one pair sorted out. And for the other, I don't want it to be that number at all. That number shouldn't be coming because I want only one pair, exactly one pair. So whatever else I am getting is from the other 12 numbers. And once I have chosen those three, say I get two, so say I get an ace here, right? I get two aces, say of hearts and of clubs, and then I get a 2, a 10 and a jack in this 12 threes, C3. All right, I get a 2, a 10 and a jack. And now these can happen in 4 ways each. By that I mean, by why I'm saying that is, I can get two from any of these four choices of different types of cards, 10 from these four, and jack from these four. So there are four possibilities there, four here and four here, and hence I have to divide and multiply it with 4 cube. My denominator is still the same, and hence now my answer, the numerator is, I choose one from the 13 different numbers I can get. Say I get an ace, I get a 2, I get a jack, whatever. I have 4 of those. So I choose 2 from that. That takes care of my pair, that exactly one pair that I want. And now from the leftover cards, I choose 3 different cards. Say I get a 2, a 10 and a jack. And since I want only one pair, I have to choose 3 different numbers. So that's why I'm doing a 12C3. I'm choosing from the 12 leftover, I'm choosing 3 different numbers. And each of those different numbers can be from 4 different, can have 4 different, there are 4 cards for each of those, right? So I have to multiply with all the options that are there for those cards. So this is my probability. Now I would like you to solve two pairs and three pair conditions, and let me know in the comments. uh, I'll solve this problem next, but I want you to try to solve C, D, and E by yourself. It is similar to what we did in D, and I will come back to the answers too for this. All right. Yeah, I will continue this in the next lecture because I think this is enough for this particular lecture and I wanted to understand this in depth. I will continue it in the next lecture, and yeah, thank you all. Let me know in case you have any issues. I can explain anything again.